We're going to be in the setting of the two-dimensional sphere with the usual metric, and we'll have the Laplace operator acting on the L2 space, and it's been known for a very long time now that the spectrum is given by these numbers. And you can write down an explicit orthogonal basis in terms of these generalized Legendre polynomials. You just take a character in the longitude direction, and then you need to solve a PDE in the latitude direction, and that is then solved by these generalized Legendre polynomials. And they look as follows. Here are two examples. So here red means a very large value, and blue means a very negative value, and green is around 0. I should mention that these pictures are all going to be qualitative, and the reason for that is that in particular this function here is very large at both north and south pole, and if you were to make it to scale, then the other functions would essentially just be green. So as you can see, kind of like how they're defined, they have like really nice rotational symmetry, but because also again how they're defined, they have like these very large kind of like, they're not poles, but like masses concentrate very much at the pole, north and south pole here, and in these sort of regions here. Okay, and so the question is, can you find like objects which distribute their mass a little bit nicer? And these Hecke Eigenforms come into play. So let me give you some intuition for Hecke operators. So one way to define the Laplace operator is as follows. And if you take an average over the boundary of a small spherical cap around your point, and then let that small spherical cap go to 0. And then you can do the same sort of thing discretely. In order to do so, you need to identify the sphere with the projective trace 0 Hamilton quaternions. So that just means the real part is 0. And then you can define the nth Hecke operator again as like some average, where you take the integer quaternions with norm n, and you precompose with the adjoint map, which is just going to be some rotation. As the Laplace operator, these Hecke operators, they're self-adjoint, and moreover they commute with each other and with the Laplace operator. And so you can find a common eigenbasis. And so the question is, how do they look like? And in some sense they look like a weather forecast for Jupiter, like this, and kind of this is the same eigenspace 42 as the other two images before that you can kind of compare. But again, I should mention the colors are not to scale. Right. Yeah, so you can kind of see that they have like some sort of different, maybe somewhat mysterious symmetrical properties. And it's believed that they have like really nice distributional properties. And so kind of what are the questions you can ask? So you fix a Hecke Laplace eigenfunction psi, to normalize it, and then you can kind of ask the first sort of question is, what are the LP norms along a sequence when your eigenvalue goes to -infinity? And here you have conjectures of Berry and others that this should behave for even integral moments. This should behave like a Gaussian with mean 0 and variance 1. And the largest power which we've been able to prove is 3, which is famously not even. So you kind of need to get rid of the absolute value, and that is a result of Böcherer, Sarnak, and Schulze-Pilow. Another sort of question you can ask is a question of quantum ergodicity, and that kind of like just asks what are the limiting measures of phi squared against the Haar measure. And here the bigger conjecture here is that you have a quantum unique ergodicity, meaning that any sort of limit you will take, you will get back the Haar measure. And here you have results of Zeldich and Darajan that for a lot of these subsequences, it does actually converge to the Haar measure, but we haven't been able to prove it for all. All right, cool. So I would like to look at the infinity norm now. And so immediately you run into the first problem, that we understand the weather better on Jupiter than we understand an individual Hecke eigenform. So what you have to do is kind of you embedded into a family here with like common eigenvalue of the Laplacian. But then you want to understand like an individual one. So one way to do it is again look at higher and higher moments, and then kind of if you're able to take an arbitrarily high moment, then of course you get back the supremum of the whole space. But this is very hard, and so what you instead can do is go to a moment which we understand very well, and that's the second moment. And there you can kind of amplify or mollify, kind of you try to understand or construct things like this, which you do understand. And so the hope here, also the idea of mollification, amplification goes back to Selberg, and I think even further. And the idea is that you single out one function which you want to get like a good bound, and then you hopefully are able to construct these amplifiers in such a way that the amplifier of the function you want to consider is very large, and the other ones are just positive, and so you can kind of throw them out afterwards in the bound you get. And for Hecke Eigenforms, such an amplification method has been shown by Ivanic and Sonak. And so the way you do that here is you kind of take a pre-trace formula, so like a second moment, which you do understand, and then you apply these Hecke operators to it, and then you can take a particular linear combination of it, and then I will give you an expression like this. Okay. Using that idea of the Ivanic-Sonak amplifier, Van de Kam was able to show the following result, that the sup norm is bounded by the eigenvalue, or minus the eigenvalue, to the 25 over 24, which I've written as a quarter times 1 minus 1 over 6. Here, the quarter, if you remember earlier, that the Legendre function had like these large poles had large values at the north and south pole. That exactly goes up to the size of lambda to the 1/4. Okay, and moreover, you're able to show that this is really kind of the convexity bound, so you're able to show that for any sort of function on this space. All right, and so for the Hecke Eigenforms, Van de Kam managed to save this 1 over 6, which is kind of what you always can just only hope for using the Ivanic and Sonak amplifier. And so here's now a new idea. So instead of just taking like one amplifier, you can parameterize them. And so now you assume that these parameterized versions, they lie in some common Hilbert space. And moreover, that they preserve orthogonality. Right? Once you have this, you can take the norm in this Hilbert space, and the norm squared, and you end up with the following expression. So you end up with a fourth moment, which is kind of amplified by these norms of in your Hilbert space, right? And so the big question is, of course, does such an object exist? And the answer is yes. So here, in this example, you can take what is known as a theta lift, which you can construct from the Hecke operators again, and that's a cusp form on the modulus surface, right? And so in this particular case, we really understand what these norms are due to Ivanic and Hofstein and Lockard, and so you can, for purposes here, you can just pretend that they're one, and so you end up with kind of a fourth moment. And so the question is, what can you prove? Turns out if you look at the geometric expression, there's some cancellation going on S2, which I can't quite grasp, but if you go up one dimension higher on S3, the same sort of techniques work, and managed to prove the following result, that the supremum norm is bounded by lambda to the 3 over 8. And here, again, this convexity bound, in this case, is lambda to the 1/2. And this on S3, instead of the Legendre polynomials, you have the Chebyshev polynomials of the second kind, are kind of the eigenfunctions. And they have exactly these large poles again of like lambda to the 1/2. And so to compare it again, as I was mentioned, the best thing you could hope for with an Ivanic-Sonak amplifier is getting a minus 1 over 6 here. But here you manage to get a minus 1 over 4. And actually more generally, as this comes kind of from a fourth moment estimate, you have a more general theorem. The problem here is though that these amplifiers are not perfectly orthogonality preserving, so the statement is a little bit more complicated and deformated. Whilst I'm here this year, I plan to use this idea in collaboration with Ilya Kyutin in various other settings and for other problems that I've alluded to, distributional problems. Okay, yeah. Thank you for listening.